Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're doing quantum chemistry. So we're going to be smart. We're learning quantum physics in chemistry class. So this is where it overlaps. And this is chemistry class, and we're finishing the notes that we started Monday. So this is part 2. Go back and watch part 1 if you didn't see it. All right, so we just did this example problem of how to figure out molar mass. And it's a weighted average because the percent abundance is not the same all over. So we're not going to do the second problem. I'm going to let you do it, and then I'll do it, and you can check your answers later. So what we want to go down to is where it says quantum chemistry, or quantum physics is what we're doing. Okay, and this is the modern view of the atom. And our new view of the atom is that electrons can be described as a particle, like a tiny little particle, or even a wave. They have so little mass that they can just sort of be thought of as light. And there's a relationship between lights and electrons. And you already knew that, because if you want to turn on a light, what do you turn on? The electricity, right? No electricity, no light. Now, how did they figure out that there is a relationship between, this is not working. I'm getting too much light here. Stop it. Shh. How did they figure out there's a relationship between electricity and light? And the experiment was a couple of things. One is they shined a really bright light on some metal and it splashed out electrons. And then also another one is they were able to use, so that showed one relationship. And then another one is they were able to use electrons with no air at all, just a beam of electrons, would turn a paddle wheel, and also light could turn a paddle wheel. So light must have some substance to it in a way. And it's because there's a relationship between a photon and an electron. The photon is the energy that is given off by an electron. So I have this illustration. Now, my illustration is not the real equipment because it's expensive and my equipment was cheap. But what it is, I'm going to use light, just like they did, to turn this paddle wheel. And y'all can't see it, but I'll show it to you in a second, because when I tried to hold it, I messed it up. Okay, so you see the little paddle wheel right here? I'm going to shine this light on it, and I'm going to make it turn faster. See, I'm not doing anything but shining this light on it. The light is making it turn. Do you see that? So there is a relationship. If it was just light with no mass, it could not make that turn. But it's making it turn pretty fast, isn't it? So let's see if I can kind of show the people. What I did is I used this, and I shone this flashlight on it, and I don't know if you can see it, but it's turning really fast from the light, much faster than when it was just standing here. While I was holding it, it was getting light from outside in that fluorescent light, and it was turning too much. So I moved on my desk where it wasn't right under it, but it is doing great now. It's zipping along. Okay, so that's not everything that happened in the real experiment is going on there. There's more to it. For one thing, it's not under a vacuum. There's air in there. In the real experiment, there would be no air. But it illustrates what was going on, okay? So electrons can be described as a particle of a wave. We already learned in our video they can jump between energy levels. If it jumps between like that first blue line and the second one on our Bohr model, remember in the video it'd go whoop, whoop, that it would jump down between that. So when it jumps, it's called a quantum leap. And when it's at the lowest energy state, it's called the ground state. You can excite an electron with heat or electricity. And if you do, it is in the excited state. So if an electron jumps up from where it was to a higher level, it's excited. It's a happy electron. Okay, and you can calculate. Now, this was left off of your notes, so make sure you write it down because it's on the test. The guy who started figuring all this out was Max Planck. His mom gave him a bold name, didn't she? Max Planck. If my last name was Planck, I probably wouldn't name my kid Max, but she went for it. Max Planck. It's just a little too rhyming. He came up with the famous equation, E equals HV. And it shows that there's a relationship but here, mathematically, that you can calculate. So he is considered the father of quantum mechanics. What we are learning is called quantum mechanics. And H is Planck's constant. So where that's not in your notes, make sure you write it down. Everybody got it? Max Planck, his formula, H equals HV. H is Planck's constant. You can calculate the energy between these levels. Now, when the electrons jump up on an energy level, eventually they jump down again. They go back to ground state, and they have to give off that extra energy. Does anybody remember how they give off the extra energy from our video? What did they give off? I'm drawing it like how it was drawn in the drawing.
Beta something.
That's for nuclear chemistry. They gave off light. They'll give off the extra energy as light. And not just visible light, all the light. Remember in the video, he had the little needle and we were along and went whoop. And it was UV light that the electron was giving off as it jumped back down. Do you remember that part of the video? Remember I told you we're going to talk about that video for the rest of the semester. It could be Ronald McDonald is very ugly, extra gross. It could be any of them. Radio, microwave, infrared, visible, UV, X-rays, gamma rays, all of them can be given off as extra energy in this. And you know, the visible is Roy G. Biv. Roy G. Biv is a colorful man at the rainbow's end. Do y'all know that song? Yes, every time there's somebody who knows it. They might be Giants. Their science CD. It's the one that has electric car and 3/4 of George Washington's head. If you missed it, you missed out in your childhood. You didn't get the science songs. You needed the science songs. All right, so I'm going to scroll this. Are we good? Can I scroll? All right. Good job. Y'all are doing great so far. You're going to learn something you've never learned before. School is often boring because you learn the same old things over and over again, don't you? Today, you learn something different. All right, so quantum numbers. Okay, so I could send a letter to you, and out of all the 9 billion, 7 billion, however many billion people we have in the world, it would go to you. So I could write down that you're in the United States, and it would rule out every person who's in every other country in the world. I write on your address Georgia, and it rules out the other 49 states. I write down Dallas, and it rules out all the other cities in Georgia. I write your street, and it rules out all the other streets in Dallas. I write your house number, and it rules out all the other houses on your street. I write your name, and it rules out everybody else in your family. So out of all the people in the whole world, that letter will go to you with your address, right? You understand that? Well, electrons have addresses, and I can write down 4 numbers that will tell me which electron it is in the atom. And they are called the quantum numbers. Dun, dun, dun. All right, so honors is going to have to know, I will point to one electron, and they will have to give me the address. They'll have to give me the 4 numbers. Y'all aren't going to have to do that. We make them earn their H. Their other half a credit. We have to make them earn it, right? So, but I want you to know what they are, because when you get to college, you might have to write the numbers like honors. So I want you to at least know what it is. But you're not going to be held accountable the way they are. They're going to have test questions. This is what you have to know. Okay, the first number is called the N number, or it has a special name. It's called the principal quantum number. A lot of times in math, lowercase n means number. Have y'all noticed that? It's on your calculator. If you've got the TI graphing calculators, it has an N on that button that has X. It's XT, which is tall, circle with a line through it, which is theta, and then a lowercase n. That lower n stands for number. Y'all gotta stop talking, or else I'm gonna make you go to the back. We'll be back in the back. I could say in the back Jack, but it wouldn't be Jack. Jack would stay up front. All right, So the first number tells what level it's on. So the electrons can live on 7 levels. And it's like an apartment building with 7 floors. So here's my little apartment building. See how it's got 7 floors? There are 7, and we know about 2 rings on our Bohr model we did. There's really 7 of them. 7 rings, 7 levels that the electrons can live on. So that's the first quantum number. It goes 1 through 7, and it tells what level it lives on. The second number is designated by a cursive L. Did y'all have to learn cursive in school? For a while, they didn't make people do it. When I was young, we had to learn cursive. When my kids were young, the oldest, they didn't make them learn cursive. But now it seems like it's back again. So it's a cursive L, it looks like that. And it tells the shape of the orbital. The orbitals come in 4 different shapes. They are called, and the numbers that correspond with them are 0, 1, 2, 3. But the shapes are also called by a letter, S, P, D, and F. The S shape is sphere shape. S for sphere. That's a little hard to say. So the number for it is a 0, because zeros are also sort of like little spheres, aren't they? So, and there's only one type of S orbital, and it's just a ball, okay? The next kind of orbital is called P-shaped, and it really they say it's dumbbell-shaped, but it really looks like you take a long balloon and twist it. And I have never seen anybody lift weights with anything that looks remotely like that. So I don't know why they call it a dumbbell. But it's got 3 ways that it is shaped. It can either be on the x-axis, oriented, the y-axis, or it can be z-axis. So there's 3 of them. One sideways, one up and down, and one coming out at you. Sort of looks like a number 8. So there's 3 types, X, Y, and Z. The next one is called D, and don't worry too much about these drawings because they're later in your notes, because I knew these were pretty bad. So the next one is D, and D looks like a fat plus sign. It can be on X and Y. It can be between X and Y. It can be on Y and Z. It can be between Y and Z. Or it looks like these 2 baby pacifiers stuck together. So there are 5 different D orbitals. How do we feel about that? Jace, put your phone away. Listen, you're learning something brand new. This is something nobody in here but me knows, and I'm imparting the knowledge. Isn't it fun, though? School gets a little boring. Shh, don't tell anybody, because you learn the same thing over and over again, and today you get to learn something new. It's so exciting. The last type of orbital is designated by the letter F, and they're F because they're just kind of fuzzy. And there are 7 different ones, and we're not really going to learn too much about them. You can learn more in college if you're a chemistry major. Even regular chemistry people don't learn much about them. It looks like a horse. That's 2 of them. 1, 2, 3, 4, 5, 6, 7. Those 2 look like a horse. So there's 7 of them. All right. So let's roll up, and you'll see the better pictures of this. Okay, so that's a better, like a real artist made them, not me. See, S is sphere, P dumbbell, D fat plus, F kind of fuzzy. Okay, so there are 2 more numbers. The third number is M sub L, which tells which orientation is it. Like for the P, it's going to let you know if it's X, Y, or Z. For the D's, it lets you know if it's X, Y, or between X, Y. So that's the third. So it's M with a subscript of a cursive L. M sub cursive L. And the fourth one is an M sub S. And this tells you if there are 2 electrons in the same orbital, that the most an orbital can have is 2. And if they're having to share a room, they spin like a globe on its axis, like the Earth's on its axis. One will spin clockwise and the other one will spin counterclockwise. So those are designated by +1/2 or -1/2. Do y'all have a question? I see one. All right, can I scroll? Good. Y'all are doing awesome. Y'all are going to get much more time for your lab than honors did. Because I made them learn how to do those numbers. All right. We're going to learn something called electron configurations and orbital diagrams. It's a brand new thing you've never learned before. Okay? And we're going to spend the rest of the period learning how to do this, including doing an activity. So part of this, I'm going to tell you, and it's not going to make a lot of sense until you do the activity. So don't panic. You're going to be fine. Okay, so here are the rules. The first one is called the Hund's rule, and it's in orbitals of equal energy, they each get an electron before they double up. I call this the kid rule because it's like kids sharing rooms. So like husband and wife get married, and they buy a 3-bedroom house. They take the good bedroom, the master with the bathroom. Okay, then they have a kid. He gets the next best room. The one with the good closet, he gets it. Okay, then they have another kid, and he gets the other room. Not quite as good of a closet, but he still gets his own room. But then a third kid comes along, and somebody's going to have to share a room. They each get a room before they double up. Right? Is that pretty much true in real life? Now, my boys are weird. My youngest two would rather share a room than not, and have the other room to be the man cave. And, you know, have the big screen TV, all the gaming devices, the Xbox, the PlayStation, the Wii, what's the new one, Switch? New one. So that goes in that room. And their computers in there and all that stuff. They'd rather have the nice room because they just sleep in their room anyway. They don't care about that. They're real close in age. They're less than 2 years apart, and they're good friends, so they get along, unlike some kids. All right, so Hund's rule does not apply to my children, but regular children follow Hund's rule, right? Okay, the next one is called Pauli's exclusion principle, and it's if they share an orbital, if they share a room, one spins clockwise and one counterclockwise, and that is shown by plus and minus a half, or it's shown by one arrow up and one arrow down. Okay, everybody understand what that is? An arrow up and an arrow down. Yeah. Okay, the third rule is that the lowest energy level fills first. So if you think about it, if this is a house, notice there's no stairs. They have to hop between levels. It wouldn't have been, if you were an electron, try to imagine yourself as an electron, wouldn't you rather not have to do all that hopping? So you would rather live on a lower energy level in general. Yeah, all has to do with energy. And this is called off-ball principle, and I think I left it off your notes, so write it down because it's on the test. Off-ball, A-U-F-B-A-U, off-ball principle. That's fun to say. All right, now, look back at our house again. Get up close so people on the TV can see it too. All right, so notice how these S rooms are very big. Oh, let's get you a new one. Notice how these S rooms are very big. These nice big sphere rooms. The orbitals do not just fill from the bottom to the top. Sometimes the electrons would rather jump up another level for a nicer room. This chart tells what order they fill in. 1s fills first, then 2s, then 2p, then 3s, then 3p. But note, 4s fills before 3d. See these little cramped 3D rooms? Can you see those? They're little and cramped. You're going to see them in a second. It's nicer for the electron to jump up to 4 and get a nice S room instead of being cramped in that 3D room. It's worth the jump. Does that make sense to you, Jace? You're staring at your lap again. I bet it's your phone. I'm just guessing. Put it away. Put it away. Pay attention. This is not something you know how to do. I promise you, you don't know how to write electron configurations yet. I'll sing you the song, but you got to learn it. It's on your test Friday. Something brand new. All right, so that's the order it fills in. Now, some people write this chart. They put all the 1S's, go over, skip 1, then the 2's, then the 3D's, then the 4F's. But when students do this, they mess up and fail the test. So I call this the baby way. And you're not going to do it the baby way. I'm going to teach you the real way to do it using the periodic table. And that's why I gave you a periodic table today. Did everybody get one of all those papers over there? All right, that periodic table is going to be your cheat sheet. From now on, we're going to write certain things on that periodic table, and you're going to be allowed to use it on the test. And you can write other stuff on it. If you just need to remind yourself of something, you're going to be allowed to write it on that periodic table and use it on the test. So this is a cheat sheet that you're going to work on. I gave you a good start on it, and it's going to be very helpful on tests. So don't lose it. Keep up with it, and you might want to go back and color it, color the different sections of it, or maybe label it somehow. But that's up to you. This is your cheat sheet. I'm not going to take it up. You're going to use it. Okay, also, there is an abbreviated way to write these that I'm probably not going to teach you today. I'll probably teach you tomorrow. But it's called the noble gas configuration. It's a shorthand way to write these electron configurations. Okay, do I want you to move yet? No, I'm going to leave you where you are. Okay, so let me show you how to do this. So what you do is you look at the periodic table, and it's going to show you how to fill in the chart. Okay, so I've got my periodic table, and so it's hydrogen, and notice that there are 7 levels to the periodic table. Do you see that? Look at my periodic table on the wall. Do you see those numbers, those red numbers I wrote on the left, 1 through 7? They also had them written in blue, but I wanted to make sure everybody understood. Those are the 7 levels in the apartment that the electrons can live on. Okay, so hydrogen only has 1 electron, and can you see the red number 1 out beside it? It lives on the first floor. And it lives in an S-shaped room, because if you look on top of that periodic table, do you see, look at these letters. Sorry, TV people. Here are the letters that tell the shape of the room that the last electron lives in. S, P, D, and F. So you should write this on your periodic table too. S, P, D, and F. Write it right where I wrote mine. Okay, so we know, because hydrogen is under S, that last electron is in the S room, and there's just 1 electron, so we get an exponent of 1. So this is the electron configuration for hydrogen. You're going to learn how to write them for all the elements. Somebody already knows how to do it? Did somebody say they know it? Yay! Awesome! You got a leg up then. Okay, so here's helium. Helium, for just this, we pretend like it's over there sitting next to hydrogen. See on the periodic table how there's a little space where helium could go right there? For this, we pretend it is over there. So because it's 2 electrons, both of them go into the sphere-shaped room on the first floor. Both electrons of helium go in there. So let's do another one. Okay, so lithium, its first 2 electrons go on the first floor into the S room. Notice how lithium is on the 2nd level. See how there's a 2 next to lithium? Right on the big periodic table, there's a 2 right there. It's on the 2nd floor. And its electron goes into an S-shaped room. So its first 2 electrons go on the first floor into an S room, right down here. The next electron goes up here into that room. Now nickel's a little more. So how you do it, I'm going to do it over here, and then I'll do it here for the people on TV. Okay, so we're going to do nickel. Nickel is number 7, and you go left to right, looking at the letters, looking at the numbers, and you can write it. So you start with hydrogen, 1s2, 2s2, 2p, 1, 2, 3. How do we feel about that? So 1s2, 2s2, see I hit two places, 2p, 1, 2, 3. Nickel, 1s2, 2s2, 2p3. Let me do it for the people on TV. The people who are out today. You do it like this. 1s2, 2, it's on the second floor, s, let me write on this one for you. Okay, now I can show the TV people. Okay, so we're going to do hydrogen. 1s1. Helium. 1s2. We counted 2. Lithium. 2s, forget that. Lithium. 1s2. 2s1. Now we're going to do nitrogen. 1s2. 2s2. 2p, 1, 2, 3. 1s2, 2s2, 2p3. We're going to do an activity on this that you're going to get better at. All right. Shh. Get quiet again. All right, now light emission. You already learned about this in your video, that when the electrons jump up and get excited by heat or electricity, they jump down again. And when they do, they give off the extra energy as light. And because each atom has unique orbital patterns, every element has a different number of electrons when it's an atom, not an ion. If they jump out of those orbitals and give off light, they give off a unique broken rainbow. It's like a rainbow with just little bands, each band representing where an electron is jumping off and giving off its extra energy. And because they're all different, it's like a fingerprint where you can tell which element you have by which broken rainbow it gives off. And we're going to do a lab with that on Thursday.
Hey, Miss Olivia wants to know if you have 2 pieces of this paper.
Yes, come in. Right there, see that cabinet that says fire blanket?
Yeah.
They're right there. Help yourself. All right. Any questions about that? This was from our video. Everybody understand it from the video?
Thank you.
Okay, so next, chemical versus physical property. Remember, triangle is the Greek letter delta. Oh, I need to tell you there's a song that goes with the orbital diagrams. Okay, it goes like this. 1s1 and 2s2, and then comes 2p6. I said it wrong. 1s2 and 2s2, and then comes 2p6. Electron configurations, yes, they're really slick. Nobody's heard that one? Oh, well. That's a good one. At least y'all had heard Roy G. Biv is a colorful man at the rainbow's end. All right. So a triangle is delta. It means change or difference. So a chemical property is how something changes when it goes in a chemical reaction. A physical property you observe without changing the element. And emission spectrum, this broken rainbow, this fingerprint, is a physical property. We're going to do more with physical properties and chemical properties, just sort of off and on throughout the semester. I don't really put it in any one unit. The other thing you need to know is the states of matter. Another physical property is states of matter, solid, liquid, gas, plasma, like in the fluorescent lights and in lightning. Well, more about this, we'll redress this when we get to thermochemistry, unit 8. Okay, any questions about that? That is the notes. Now, I'm going to keep the video going because I want the people on video to understand how to do the worksheet and the homework that you're going to do. So, what I want you to do now, well, maybe I'll put a different video because otherwise they're going to have to wait in video land for y'all all to move around. Okay, so we're going to end this one and I'm going to restart it when I explain the homework. So like, share, subscribe. Science is great. Yay!